Hello everyone, and today we will see the Engineering Service 2021 mains exam that has been conducted in November. So this is a video 2 and we will solve one question of paper 1. So this is a very conceptual question and your fundamental that is the of regarding counterflow and parallel flow will be get cleared by this question. So what is said in a double pipe parallel flow heat exchanger, hot fluid enters at 120 degrees Celsius. Okay, so write down here 120 degrees Celsius and leaves at 80 degree. Okay, and cold fluid enters at 20 degree. So here write down 20 degree and leaves at 50 degree. Okay, and if the inlet temperature and or heat transfer coefficient, that means inlet temperature, suppose now let me write down something th1, that is inlet temperature for hot fluid, th2, that is exit temperature of hot fluid, tc1, that is inlet temperature of cold fluid, and tc2, that is exit temperature of cold fluid. And overall heat transfer coefficient will be same and flow rate will be same, that means m dot will be same. If and we have to find the exit temperature if the fluid arrangement is counterflow arrangement is used. Use effectiveness method. So what this question says, initially the heat exchanger, double pipe heat exchanger, it is a parallel flow heat exchanger, and these are the result of inlet and outlet temperature. But what it said, this inlet temperature of hot fluid and inlet temperature of cold fluid remains same, u will remain same, the mass flow rate will remain same, and heat capacity of the both the fluid will also remain same. So if we change this configuration from parallel to counterflow, then what will be this exit temperature for hot fluid as well as cold fluid? So now we will use a heat balance equation. So whatever heat is uh, rejected by the hot fluid is gained by cold fluid. So that is mass of hot fluid into Cp of hot fluid, or C of hot fluid, not Cp because it is a liquid. So we will write C, and Th1 minus Th2 is equal to mass of cold fluid, or we can into Cc, that means heat capacity of cold, specific heat of cold fluid, that is multiplied by Tc2 minus Tc1, and Mc collectively we can write it capital C as a heat capacity. So Ch, and what is the temperature difference? That is 40 degree here. 120 minus 80, that is 40 degree, is equal to capital Cc, that is heat capacity of cold fluid, and this temperature difference is 30. Now to equate this both the sides, Ch into 40 and Cc into 30, the Cc must be greater than Ch. Okay, so here we can say that what is the C minimum? The minimum heat capacity is Ch and maximum heat capacity will be Cc. Now what is the capital C, that is heat capacity ratio, that is C minimum by C maximum. That means it is a Ch divided by Cc. What is minimum here? C Ch. So Ch by Cc, because heat capacity ratio is ratio of C minimum by C maximum. So Ch by Cc will be 3 by 4, or we can say that 0.75. So this is our one of the result. Mark it and put it aside. I'm writing over here C is equal to 0.75. Now what is the effectiveness? The definition of effectiveness is maximum possible heat transfer and actual heat transfer. Okay, and maximum possible heat transfer will when possible, that means the maximum when there is a maximum temperature difference, that is Th1 minus Tc1. This is the maximum temperature difference, 120 and 20, and heat capacity should be low. So heat capacity will be Ch, and the actual possible heat transfer is Th is equal to Th1 minus Th2. The actual difference is 120 minus 80, but the maximum possible temperature difference is 120 minus 20. Here CH will get cancelled out. Effectiveness is what? 40. This temperature difference 120 minus 80. 120 minus 80 divided by 120 minus 20. So it will be 0.4 or 40%. Sorry, 0.4 or 40% effectiveness. Now for parallel flow, the equation is given in the question paper itself. So the parallel flow heat exchanger effectiveness formula, 1 minus e power uh, 1 minus e power, let me see here, into minus n into 1 plus c divided by 1 minus, sorry, divided by 1 plus c. So for parallel flow heat exchanger, 1 plus c. So here we have effectiveness 40% or 0.4, 1 minus e to the power n. N is NTU into 1 plus c. Heat capacity is 0.75, 0.75 divided by 1 plus 0.75. So here unknown we have n. So when you solve this, but please be careful while doing the calculation, because there is a chances of error here maximum. So n, you, or you can say that NTU, number of transfer unit, will be 0.688. So now keep one thing in the mind, that whenever you change the configuration from parallel to counter flow, your NTU will not be going to change, that will remains constant, and the heat capacity ratio C, that is C minimum by C maximum, that is not also going to change. So we will use the effectiveness formula for counter flow heat exchanger, 1 minus e to the power minus 1 plus c into n upon what the formula is given. Yes, sorry, here 1 minus c will be there. Sorry, 1 minus c upon 1 minus c into e to the power minus n into 1 minus c. Okay, now we have 1 minus e to the power 1 minus c is what, 0.75, n is what, 0.688, we just found out, 0.688 divided by 1 minus c is what, 0.75, we have found out, into e to the power minus 1 minus 0.75 into 0.688. So when you solve this, and I'm again telling you, please do this calculation very neat and clean manner, or check twice, okay, or be careful, because there are a lot of chances of error, because I did this mistake the same while solving this question. So that's why I'm telling you. So here when you solve this, so you will get 0.4288, that means 42.88%. So just see the concept, we know the effectiveness of counter flow heat exchanger is greater than the parallel flow. So this is the result, because here we have found effectiveness 0.40, okay, 40%, and here 42.88%. Now the definition of effectiveness is maximum possible heat transfer. Then when maximum possible, when heat capacity is minimum, and th1 minus tc1, and ch upon into th1 minus th2. So this will be cancelled out, because heat capacity, the minimum heat capacity is itself of hot fluid, and effectiveness is what, 0.4288 is equal to th1, because here it is given that inlet condition of the both the fluid are same, so 120 minus 20. So when you solve this, you will find the exit temperature of the hot fluid, th2, will be 77.12 degree, 77.12 degree Celsius. This is our one of the answers. And again use the energy, the heat transfer balance equation, heat balance equation, that is heat capacity of hot fluid into th1 minus th2 is equal to cc into tc2 minus tc1. So cc by ch is what, 3 by 4 into th1, that is 120 minus 77.12, and tc2 is what we have to find, and tc1 is what, 20 degree. So when you solve this, you will get tc2 as a 52.1 degree celsius. 52.1 degree celsius. Okay, so now compare the results. Initially it was 80 degree exit temperature in the data, and outlet temperature was 50 degree. So the hot fluid is more getting more cold, and the cold fluid is getting more hot. So this much the excess extra heat transfer is only possible due to the configuration of counterflow, which ultimately increase the effectiveness of our heat exchanger. So this is the answer of the question, and I hope you can understand this fundamental very clearly. And now you come to the one conclusion that the effectiveness of counterflow heat exchanger is more compared to parallel, and the results are in front of you. So I hope you like this solution, and tomorrow we will see some more solutions there. So thank you for watching this video, and subscribe this channel for daily up this kind of questions.